Thanks everybody for joining today's webinar. My name is Daniel Noll. I'm the Director of International Programs at the Edison Electric Institute, and I'm really pleased to have here today Tom Odell, who's the Director of the Program Support Office of Large Projects at Toronto Hydro, to give today's webinar entitled Powering Urban Growth, Toronto Hydro's Copeland Underground Transformer Station. And so today we're going to learn about the construction and the planning and the engineering challenges and the approach that Toronto Hydro has gone to do something pretty unique, which is to underground a station in the downtown Toronto area. So really happy to have you, Tom, here to give today's presentation. And before you begin, I'll just note for all of our participants that we'll be receiving questions throughout the webinar. You can submit those questions to me as Tom is giving his presentation. You can do that by text using the chat feature within WebEx. And so as his presentation is going on, please send those questions to me, and then we'll ask as many questions as we can at the end of his presentation. So with that, Tom, I'll go ahead and turn it over to you, and we can get started.
Okay, thanks very much, Dan. Pleasure to be here today to participate in this webinar. There's a lot of folks who are really interested in the Copeland Transformer Station. It's got a number of unique features which will become evident during this presentation. But first, a little bit about Toronto Hydro. Toronto Hydro was established in 1911. It owns and operates the electricity distribution system for Canada's largest city, Toronto. It is the amalgamation of 6 utilities in 1998. The City of Toronto amalgamated many of the boroughs into one large city in 1998, and at the same time, Toronto Hydro amalgamated all of the constituent utilities in the Toronto area. The City of Toronto has a population of over 2.9 million people, and it distributes approximately 18% of the electricity consumed in the province of Ontario. Our record peak load was 4.6 gigawatts in July of 2018, and our record peak was 5 gigawatts in July of 2006. The overview, we operate $4.7 billion worth of capital assets. Our head office is at 14 Carlton Street in Toronto. We have 690,000 residential customers and 770,000 customers in total. There are 82,000 general service customers with monthly demand below 5,000 kilowatts, and 38 large users with monthly demand over 5,000 kilowatts. And we manage this with 1,400 employees. The service area, if you're familiar with Toronto, it's bracketed by Steeles Avenue, which essentially runs along where the 407 is. On the west, it's Highway 427, and then the town line with Pickering, which is in the 905, is our eastern border. Our southern border is Lake Ontario. We have one control center plus a backup. We have 15,500 kilometers of overhead wire, 13,200 kilometers of underground wire, 146 municipal substations, 17,400 primary switches, 60,560 distribution transformers, and 180,000 poles. So the challenge in the City of Toronto is urban densification. This photograph taken from Canadian Business Magazine in 2012 was part of our submission to the Ontario Energy Board when we justified the construction or moving forward with the Copeland Transformer Station. Essentially, the grade buildings were the buildings that existed in 2012, but the blue buildings were buildings that were under construction at that time. Their yellow were sales underway, green approved but yet to commence, and red the application to the city. So we recognized at that point that there was significant growth, and obviously the growth was going to mean an increase in load. That was 2012, and the OEB application was approved at that point. Bear with me. But in 2016, in our latest application to the board, we show the urban densification and what's happened. And what you can see is the number of built projects in what we call the south core of the city is phenomenal. In fact, we are essentially the largest, the fastest growing city in the world at this point. There are residential, there are other active projects that are taking place right now, but the primary thing I want to point out is that focus on the south core. It is an incredibly dense area. During the construction of our project, we watched as the towers sprung up around us. There are a few other concentrations of construction and urban densification, but nothing that can compare to the south core. This information came from the Toronto City Planning Division in September 2016. A recent review of downtown station loading shows, again, the red zone being in the south core. What's interesting about this, when we compare it to our load forecasts and our planning back at the time of the first application, at that time, the Windsor Transformer Station was red. The area that's shown as yellow with Windsor TS, it was shown as red, and there was no Copeland Transformer Station. So what's actually happening here is in the load forecast, we're showing offloading of the Windsor Transformer Station by the Copeland TS. And speaking of Windsor, this offloading of Windsor was not by accident. The immediate need for a new transformer station downtown was to address Windsor. It's a typical urban outdoor transformer station built in 1954, and it supplies customers in the financial and the entertainment district. The medium voltage switchgear is obsolete air blast switchgear, which is a reliability concern. There are no parts. We are spending a lot of time machining replacement parts to keep this medium voltage gear alive. As well, there's no spare capacity at the Windsor station or other downtown stations to facilitate a replacement program. Ideally, we would have a spare bus where we could offload at Windsor and begin some kind of a replacement program, but every bus is fully utilized due to the aforementioned growth. So what's needed is another bus somewhere in the downtown to enable us to offload at least one bus of Windsor to start a replacement program for that air blast switchgear. The other aspects of the Windsor Transformer Station that are suboptimal are the above ground construction. It's susceptible to weather, and it poses a potential security concern. It is right in that dense jungle of condominiums and large commercial buildings. So basically you look down on it from the office towers in the vicinity. So a new station is required. Now, the Copeland Transformer Station site selection goes back several years. And in fact, the construction of a transformer station is typically led by Hydro One networks, while we build the municipal stations feeding in the distribution network. We'll get into some of the history of what happened, but over a period of time, Ontario Hydro, then Hydro One, then Toronto Hydro looked at alternative locations in the South Core to place a transformer station that could address the significant growth in the area. What's necessary is that it has close proximity to the existing Windsor Transformer Station, and it needs the existing underground Windsor transmission cables are close to the Copeland TS location. Copeland TS will connect customers, maximizing the use of existing underground distribution infrastructure, so that basically we're not running a lot of distribution cable. The distribution cable is in our vicinity. It's also located near a waterfront redevelopment. There's significant construction right on the waterfront with new condominium towers going up. We're also away from floodplains and other hazards. We're not right on the waterfront. It's cost-effective, efficient, and it maximizes the use of land, which you'll see in upcoming slides. What I'd like to do, Dan, is jump to the first video.
Construction is underway at the historical Roundhouse Park. Located across from the Rogers Center, CN Tower, and Ripley's Aquarium, at the bustling corner of Reese Street and Bremner Boulevard, Toronto Hydro's Copeland Station will showcase the finest in structural and electrical engineering. The $195 million project is only the second underground station to be built in Canada, and when it's complete, it will be virtually undetectable to the hundreds of thousands of visitors the area receives each year. Construction started with the careful disassembly of the former CP Rail machine shop. The historical building was taken down, cataloged, and stored off-site. Copeland Station will occupy 50,000 square feet, 3 stories below ground, and crews have to excavate the site to reach approximately 40 feet deep to build the station's structure. This work is executed in careful stages, beginning with the shoring and excavation of the job site. This is achieved by installing Caisson Walls, which serve as a protective barrier around the station walls. The Caisson Wall is composed of approximately 400 concrete pillars, which are burrowed into the ground using a drill rig. After the shoring and excavation of soil and bedrock is complete, 2 tower cranes are installed to help crews place the structural steel and concrete, which essentially form the walls and flooring, and therefore the physical structure of the building. Crews lay down the foundation slab by pouring a mud slab, followed by a mat slab. When the foundation slab is complete, construction can begin on the walls. The walls are assembled by installing columns, concrete, and structural steel. When the structure is completed, all major equipment will be installed and connected. This includes gas-insulated transformers and high and medium voltage gas-insulated switchgear. Gas-insulated transformers are more compact than commonly used transformers insulated with oil. Next, mechanical and electrical building services will be installed and interior finishes will be completed. Then, work will begin to restore the machine shop according to heritage requirements. It will house the station's service equipment and controls. Just like the rest of the station, the machine shop's structural makeup will be built to withstand potentially disastrous events. Should a severe storm blow through, the station is designed with flood prevention measures, including the shoring wall, a waterproof membrane made of HDPE, waterproof concrete mixes for the exterior walls and flooring, and a redundant sump pump system that operates on emergency power. The ventilation stacks for the transformer station building will be visible along Reese Street and Lakeshore Boulevard and will be dressed with Corten steel panels to maintain the heritage aesthetic of the site. In tandem with the station construction, a 600-meter underground cable tunnel is being constructed from an existing tunnel beneath Front Street to connect the transformer station to the electricity grid. It will travel 100 feet below ground to remove dirt and rock, very similar to a mining operation. As the machine moves through the ground, it removes dirt through a conveyor belt and stores it in buckets, much like a miniature railway. When it's ready to be energized, Copeland Station will serve as a much-needed backup supply of power for high-profile customers in the financial district, and will provide the downtown core with additional electrical capacity to sustain the equivalent of approximately 70 condo buildings. This will provide relief to neighboring stations, which are almost at their capacities. For more information and construction updates, please visit torontohydro.com/Copeland Station.
All right, Tom, you might be on mute.
I am on mute. Thank you.
Perfect. There we go.
Okay. Do we see the slide that says Action New Copeland TS Site Selection? That's the slide we were on before?
Yes.
Okay. So as I mentioned, there was some history here. There's an artist concept that I have in my office of the Queen's Quay Transformer Station that was proposed by Ontario Hydro back in 1987. This sits in very valuable property right on the lake, and an agreement was reached between Ontario Hydro at that time and the City of Toronto to swap that land location, which is at the foot of York Street, for an option on what was called the railway lands. And the railway lands are the lands adjacent to the John Street Roundhouse, which eventually became our site. Ontario Hydro split up in the early 90s, and the transmission side of their business became known as Hydro One Networks. And Hydro One Networks did pursue a railway lands transformer station, and that is indicated on the top right-hand side. This concept is a 1992 concept. And what you'll see in the next slide is that this concept didn't have any potential for being executed because of some significant design problems. That is to say, the John Street Roundhouse was designated as a National Historic Site, and as such, heritage protection of the site was necessary. And through the relationship with the provincial government and the municipal government, many stipulations were put in place. If you look at the design, there's an overhead view of this design that shows the transformer station essentially being a cut into the John Street Roundhouse, and there's an annex to the roundhouse called the machine shop. What Hydro One proposed is to cut into the machine shop, eliminate about 80% of it, and build their transformer station at that location. They also proposed to have oil-filled transformers in the downtown, in that pit that you can see there with the roadway adjacent to it. There's absolutely no way that they would have had any success in getting this through an environmental assessment or the planning review. So in the ensuing years, through our Toronto Regional Planning Initiative, which involves the Independent Electrical Supply Operator, the Ontario Power Authority, the Hydro One, and ourselves, this issue was being studied all the while many of the sites were disappearing. And it was agreed that because Toronto Hydro has a relationship with the City of Toronto, that is that we are owned by the City of Toronto, we may have a more advantageous position to be able to build the transformer station, and Hydro One Hydro One basically accepted the idea of Toronto Hydro taking the lead in moving forward on the transformer station development. So what you see is the cofinal Copeland design concept, which was created in approximately 2010. This is a very busy slide, but it gives you an idea of just the challenges with respect to approvals and stakeholder acceptance. So we had approvals required from numerous government and regulatory agencies, and we had multi-year approval processes before procurement or construction commenced. So if you go back to 2008, there was much review with stakeholders, and the stakeholders included the Roundhouse neighbors, the City of Toronto, Hydro One, IESO. One thing I should illustrate that from a city perspective, what was interesting was the city did not designate the Roundhouse as a heritage site. So it wasn't being protected by a municipal heritage designation. so from that perspective, we thought we were okay. We don't have to satisfy the city. But it was a National Historic Site. And in that it was a National Historic Site, when we entered into our environmental assessment at the provincial level, they noted that it was a National Historic Site, and therefore there are heritage requirements that are built into the environmental assessment. So the province essentially took a role of codifying the federal National Historic Site requirements. And what they did is they essentially deferred to an expert on heritage preservation. That expert just happened to work for the City of Toronto. So notwithstanding the fact that we did not have to pass through a municipal heritage designation, we ended up in a situation where we were dealing directly with the City of Toronto when we established how we would move forward on our heritage. And that also involved the Roundhouse neighbours. The Toronto Railway Historical Association has a museum in part of the Roundhouse. The other significant activity was the Ontario Energy Board. In 2009, we got approval from the Ontario Energy Board to move forward on the environmental assessment and the conceptual design, and you saw the conceptual design on the previous slide. In 2010, we got approval to move forward with the land acquisition, which essentially meant having Hydro One exercise its option on the railway lands and then conveying the lands to us at a relatively advantageous price. And then we commenced the detailed design and the environmental assessment. The detailed design was completed in 2011 and formed the basis for our 2012 application to the Energy Board. And that application was approved in April of 2013 to move forward with the construction of the Copeland TS. At the same time, we were moving forward, as I mentioned before, the Ontario Class Environmental Assessment. There's a class environmental assessment for minor transmission facilities, and that stipulates the requirements that need to be met, including environmental study report, public information centers, agency, public and stakeholder consultations, town halls, et cetera. There was a significant amount of stakeholdering that was going on as part of what was stipulated by the Ministry of the Environment and Climate Change. At the same time, there was a kind of a handoff coordination when we saw approval from an environmental assessment perspective. The city began to look at our application for site plan approval. And we are still in the state of addressing city plan approvals and permits. The site plan approval was obtained before construction started in May of 2013. But then the cascade of associated building permits, including a demolition permit, plumbing permits, foundation permits, et cetera, all cascaded as the project moved forward. In total, something on the order of 25 separate permits, including things like road closures, hoarding permits, and that kind of thing. Significant amount of work with every agency within the City of Toronto. We also had to liaise with First Nations and Aboriginal communities, local city councillors, and then members of the general public. So I talked about the National Historic Site and what it really meant to us, and that ties into the machine shop, which again is this annex. And you can see in the bottom left-hand side the hashed white line. That white line defines the property line owned by Toronto Hydro, and it slices right through the machine shop and moves from Bremner Boulevard on the north, Lakeshore Boulevard on the south, and Reese Street on the west. Now, one important thing to recognize, and you'll see it in some of the other slides, is that we needed every square inch of space, and so we constructed from property line to property line for our excavation to place the transformer station. We also determined that we had to place the transformer station underground in order to get the square footage required, approximately 50,000 square feet required for transformers with medium voltage and high voltage switchgear, which meant we had to remove the machine shop. And the heritage requirement was that we not only had to remove it carefully, we had to put it back, and it had to be identical or as close to identical to the structure that we removed. So when construction commenced, actually before construction commenced, we had an environmental remediation activity where we removed lead-based paint from the inside of the machine shop, a little bit of asbestos and some other aspects, and then commenced the removal of each and every brick and cataloged where the bricks were coming from, interior, exterior, and specific locations. We also removed all of the windows and doors. And the roundhouse is constructed of timber frame, but the machine shop, which was built approximately a year after the roundhouse, is a steel frame building. So the steel was actually considered heritage as well. So we removed the steel, had it restored, had all of the windows restored, had all of the bricks cleaned, and stored off-site until such time as the machine shop could come back together again. The exterior and interior finishes must utilize those preserved building components, and again, look identical to what had been removed. Another challenge was connection to the transmission grid. The Windsor transformer station that we discussed before is connected to our Esplanade transformer station through a tunnel that's approximately 2 to 3 kilometers long and below Front Street in the city of Toronto. The Hydro One constructed that tunnel approximately 4 or 5 years before we started our project. And the purpose of that tunnel, is to connect the transmission grid from Windsor Transformer Station to Esplanade, and primarily to allow the flexibility to move the open point in the downtown. By the way, this is 115 kV distribution. The downtown transmission system is 115 kV. It's fed from the west and the east of Toronto, and the open point can shift from either be at the Windsor Transformer Station or be at the Esplanade Transformer Station to enable load shifts at the transmission level between those two transformer stations. When they built the tunnel, they anticipated that somebody would build a transformer station in the railway lands, and they created a knockout, essentially, or an orifice on that tunnel that would accept a future tunnel to the railway lands. That tunnel construction was left to us as well. So Toronto Hydro had never constructed a tunnel or anything of this scale before. It employed a 4-meter tunnel boring machine, Atlas Cop Code boring machine. It is 600 meters long. And as you can see on in the middle bottom, it continued its path through the route of the tunnel that is across Bremner and then up Lower Simcoe, and then connected to the breakout that Hydro One had previously created on their tunnel. It was a significant challenge in that, and you'll see some of our logistics challenges coming up, but we had a very, very small footprint to execute this tunnel boring project. At the time we let the contract, we gave the proponents the option of either deploying a tunnel boring machine and abandoning it underground, because generally a tunnel boring machine will enter, bore, and then come back up again on the other side. It's impossible to come back on the other side in downtown Toronto. So they had the option of abandoning the tunnel boring machine offside of the tunnel, or acquiring a reversible tunnel boring machine. And the successful bidder found a reversible tunnel boring machine, completed the tunnel activity, and then removed the TBM from the site. The significant amount of waste and spoils from this boring activity through the shale bedrock under the City of Toronto was a phenomenal logistics challenge, ensuring that we could move the waste off of the site and out of the congested downtown. So getting into it, it's a dense urban environment. The site logistics were a significant challenge. Traffic, tourists, many of you may be familiar with the City of Toronto, but from the animation video we saw earlier, one of our nearest neighbors is the Rogers Centre, the home of the Toronto Blue Jays. So we are impeded in our construction whenever there's a home game. We also have an aquarium, the CN Tower, and the rest of the Roundhouse occupants, all vying for the interest of keeping roads open and not having a construction impact. So we had a 4,400 meter squared footprint. Again, it was property line to property line. We managed to obtain one lane for a hoarding area for laydown, and could not obtain another. But our contractors both stated that it was not feasible to survive with a single lane of availability, and they were actually able to negotiate a second lane, a bump out during the hours separate from rush hour. So if you take a look at that top right-hand side, you can see a full lane within the site, but then we take an additional lane between approximately 9 a.m. and 5 p.m. So that we have a better chance of being able to remove those spoils or deliver materials, including obviously concrete. Because we had a reversible boring machine, it had a single entrance shaft. The shaft wasn't large enough for the entire boring machine. It had to be lowered, driven into the beginning of the tunnel, and then the trailing equipment, including controls, the train of spoil carriages. In the end, the entire tunnel boring machine was something like 60 meters long, while the initial entrance was only approximately 15 meters to allow the TBM in. Also, one of the real challenges was multiple constructors. Toronto Hydro, hired the station contractor and the tunnel contractor, and they both had separate notices of projects. And for the first time, we formally requested a designation from the Ministry of Labour for separation of the contractors. And that was a significant challenge in that they were working very, very closely to each other, and we had to ensure that they had separate power supplies, separate washroom facilities, and that they were essentially protected. All the while, with cranes delivering concrete and rebar and removing spoils from the tunnel, we had to ensure that the cranes were coordinated so that we did not have an incident between the two contractors. Again, the delivery of construction materials and electrical equipment were a significant logistical challenge. I'm going to show a video at the end of the delivery of the transformer tanks. There were unforeseen obstructions and inaccurate historical records. We had to actually shift the tunnel entry shaft approximately 10 meters south because a water main had been incorrectly shown on city drawings, and we had interference with that water main. So we had to shift everything significantly and hastily redesign the tunnel shaft. The supply and demand for construction resources was another significant challenge from our perspective. We have pictures here of the gas-insulated transformer tank being delivered to the port of Toronto that came from Yokohama, Japan. 2 tanks. We also have our German medium voltage switchgear, which was manufactured and delivered into storage. You can also see the cable basement and the high voltage cables that come out of the tunnel when the tunnel was finished and into the base of the transformer station. The other aspect is that under the Ontario Building Code, we had to ensure that we had seismic post-disaster design. That entailed a heavily reinforced concrete structure. We had large diameter reinforcing steel in very dense assemblies. So we had a transformer slab that was 500 millimeters thick. That would support the 5 of in the final configuration of the transformer station. There will be 5 gas-insulated transformers, and each of them weigh, with their associated equipment, 220 tons. So a 500 millimeter thick reinforced concrete floor under which there is a cable basement, and then a mat slab foundation that is approximately 6 feet thick. The other aspect, going back to the site plan approval, we had to convey to the City of Toronto an easement over the transformer station for the road that was there before the construction started. And that road feeds the tenants of the Roundhouse, including Steam Whistle Brewery, which receives on a regular basis fully laden water tankers for the production of Pilsner for the City of Toronto. The design comprehended that that road would be restored in place and that the transformer station structure would be able to sustain the weight of the water tankers, fire trucks, whatever may travel over top of it. So essentially, the roof of the transformer station is a bridge that can take the full load of highway vehicles. Another significant design construction challenge was flood prevention. We were very, very close to the lake, approximately 150 meters away. And we had to ensure that we had flood prevention, which included a shoring wall, a waterproofing membrane, a waterproofing concrete mix for all the exterior concrete surfaces, 800 millimeter thick concrete walls with waterproofing admix, as well as the 6 foot thick mat slab foundation. One of the challenges was that the waterproofing application was very sensitive to the weather. Was very, very difficult to do. We could not be wet and still be able to be activated by the heat of hydration of the concrete pours. We had adverse weather. We went through an ice storm and a few other significant events, and that was a challenge for the continuation of the construction. On commissioning and energization, we had significant challenges. Toronto Hydro separately contracted to supply, install, test, and commission of all the significant elements electrically. And so these subsystems, that is the power transformers, the high voltage switchgear, the medium voltage switchgear, all of our low voltage systems, high and medium voltage cables, mechanical, and fire and security, all had to be independently commissioned. And then we moved into an integrated testing and commissioning stage where we did end-to-end SCADA testing. We did current injection and protection verification. And I failed to mention that we are the landlord for the transmission system in that Hydro One delivers they're supplied to us through a switching station that occupies a footprint within the transformer station. So they have a 6-breaker switching system, 230 kV gas-insulated switchgear that affords them the capability to move that open point that we talked about earlier, wherever they may need it, and while still providing a radial feed to our 5 pieces of switchgear to feed our 5 future transformers. One of the aspects of this that was a challenge was coordination with control authorities. We had moved ahead with basic impunity while we were running through the construction process, but once we had energization, the control authority took control of the Hydro 1 side as well as the Toronto Hydro side of the switchgear in the middle of our commissioning activity, so we had to ensure that we adhered to our work protection requirements moving forward, and that added an additional layer of complication with respect to the commissioning and the energization. A couple of pictures here. I'm showing the HV resonant cable test. That was a significant challenge. We established that we would test the cables once they were installed and had to modify our high voltage switchgear. This is Siemens HVGIS, where we've removed the voltage transformers and installed bushings to enable us to test both the connecting cable to Hydro 1 and the cable that feeds the transformers. We had all of our medium voltage protection in the SCADA communications that had to be tested, and then low voltage commissioning for our low voltage switchgear. We have a triple redundant station service room with 3 2,000 kVA transformers, each of which is capable of operating the entire station. 2 of them are fed internally from the Copeland medium voltage switchgear, and 1 is fed externally from our Esplanade transformer station. One aspect of the design that is interesting is visible on the top right, and that is that we, when we got our final environmental assessment approval, we had a challenge because the initial design had a parapet wall between us and the wood construction roundhouse, and we were challenged that that is not consistent with the historical design and that we must have a continuous connection of our roof to the adjacent property. That introduced a hazard in that we could convey a fire to the adjacent roundhouse or vice versa. And the final solution to that was to install a dry sprinkler system as a deluge system to basically deluge the interface between the 2 buildings in the event of a fire. And that is the conclusion, though I'd like to show a quick video of our transformer delivery. But this is what the finished product looks like with the gas-insulated transformers in place. We have 2 transformers that were installed for phase 1. We are now in the process of executing phase 2, where there will be 3 more transformers added, 2 attached to medium voltage distribution switchgear, and 1 a spare transformer in the event that we have any issues with any of the other 4. There's a full sparing concept that will be executed to enable transformer 5 to pick up any one of T1 to T4 buses. So, Dan, I'd like to try again to share that other video. Okay, so the transformers, as I mentioned, were delivered to the Port of Toronto, and they went into storage while we waited for the structure to be complete. Then we moved the transformers from their berth in the port to the transformer station. This time-lapse only takes a couple of minutes. The planning for this event took approximately 6 months, and a large part of it was due to the fact that each transformer tank weighs 155 tons, plus the associated equipment to roll it. In the province of Ontario, you cannot have a load without engineering. You cannot have a load over 85 tons. So we chose a route that did not go over any structure. However, in the 11th hour, we were planning a May delivery. In the 11th hour, the Toronto Transit Commission indicated that we were actually traveling over an underground LRT tunnel that they had concerns about. So we had 18 engineering studies done about the transit of our transformers over this tunnel. We executed the transit at 2 o'clock in the morning from the port, and had to stop at the tunnel and have vibration monitoring and deflection monitoring in place. We transited the tunnel with no deflection after all of the engineering had been done. The other challenging aspect here, as you see, is the use of 2 tandem cranes. There's 550 and a 650-ton tandem crane with separate operators operating a ballet of chasing this or dropping this 155-ton transformer tank into the station. It went through an opening in the roof with about 18 inches to spare, and it was a very exciting activity. Overall, the entire delivery event took 2.5 days, and we had a 2.5-day road closure to ensure that that could happen. With that, I am complete. I just, Dan, I'll turn it over to you.
Yeah, thanks, Tom. I don't know if you want to maybe share your screen back just in case any of the questions, refer to specific slides that you want to go back to. But, we have about 5 minutes to go through a couple questions. But one thing I just want to maybe flag for some of our audience is that, I think that time lapse there it really gives a great visual to the complexity of that stage of the construction and installing those big transformers. You have another excellent time lapse on your website with the Earth Cam, which shows a time lapse of the whole site construction, the excavation and the construction from 2013 until 2019, which is also quite wonderful. I think it also gives a really good sort of visual to all of the work that went into the whole process. It's really quite powerful.
It's also very interesting because you can watch the condominiums growing in the background as we're constructing the transformer station. So,
yeah. The first question that I wanted to ask you it goes back to one of the things you mentioned at the very beginning about the rapid growth and densification that Toronto is experiencing, and you talked about this towards the end about the growth plan for this transformer station to add more transformers, and I wanted to just maybe ask you to elaborate that on a little bit about how you see the energy needs of downtown Toronto evolving over the next several years, the next decade and beyond, and how upgrading and expanding this facility is part of a plan to meet those requirements.
Yes. So the original application indicated that we had an immediate need for a transformer station in order to offload the Windsor transformer station and install capacity for a massive amount of growth in the South Core. However, in order to be prudent, our forecast was looking out to about 2020, and we felt that 140 MVA of capacity would suffice to offload Windsor and address the load growth to the 2020 period.
And what was the capacity of the Windsor station?
Oh, the Windsor station is in excess of 300 MVA. It has 6 medium voltage buses that, as I mentioned earlier, are completely utilized at this point.
Yeah.
So we are not replacing Windsor. We are replacing one bus of Windsor in order that Windsor can be offloaded and that the modernization of the medium voltage switchgear at Windsor can happen. Okay, so that's one completely separate goal of the Copeland Transformer Station. And as we speak, we are proceeding with Windsor Transformer Station load transfers to start to offload that bus and provide the opportunity for the upgrades at that location. What we've seen, it's interesting because I'm not on the distribution side, but I'm engaged because of the direct relationship and the work that we're doing on the Phase 2 application. But the expectation is that the entire capacity of Copeland Phase 1, that is 2 transformers, will be met by approximately between August to October of 2021. And so at that point, we will need new capacity. And a large part of that is feeder positions. We do not have the feeder positions in the downtown to meet our needs. So we have made, we fully expected that the transformer station would be energized much sooner than it has, and have had to make a number of mitigating changes in the distribution downtown to address load growth. As well, we're facing load growth beyond 2021, so we desperately need the expansion that was originally planned in the structural design. So we anticipate that the execution of Phase 2 of Copeland will be beginning as well. So we're doing work on it right now, but we're out on the street with an RFP, and the work will commence early in 2020 as soon as we have a positive decision from the Energy Board, and take us to the 2023-2024 timeframe within our 5-year rate application, and at that point be able to meet the growing load, the additional growing load in the South Core.
Thank you. Yeah, really helpful. When you were designing, this transformer station for an underground facility, does undergrounding the station itself, does that influence the sort of choices of what technologies and what equipment you located within it, from the buses and metering equipment and so forth? Are there any unique aspects to undergrounding that influence those decisions?
Yes. So let's see. The original concept design called for a station that was approximately 30 feet deep with essentially one floor. And as the design evolved, it was recognized that we needed more space. And the depth of the station went to 40 feet below ground. Even so, traditional oil-filled power transformer was problematic because an oil-filled transformer obviously has the concern of the combustibility of the insulating oil. And as a result, there's a significant amount of structure in order to ensure that the structure itself can withstand the potential for disastrous fire. As well, the structure has to be able to allow the escaping gases in the event of a fire. So the design to accommodate oil in an underground installation is very problematic. So the choice of undergrounding led us to the choice of everything being gas insulated, with the exception of our medium voltage tie breakers. So we ensured that we, and primarily it's the transformers. The transformers do not have the same volatility. The sulfur hexafluoride gas is the best insulator known to man, and also does not represent a flammability hazard, and therefore would fit in the space allotted. Notwithstanding that, we still didn't have enough space, so with the reconstruction of the machine shop, we established that we would occupy the machine shop for our station service equipment and for our protection and control equipment and the protection and control equipment of Hydro One. So approximately 60% of the machine shop is occupied by electrical equipment.
Wonderful.
And another point about that, we have a little bit of experience of protection and control equipment being under grade, and we don't like it. So the idea was we would take all of the sensitive electronics in the station and have them above grade in the event of a flood.
That's great. I'm going to ask just one final quick question and ask for a quick answer so that we can wrap up. But we did have one question just come in asking how the heat generated from the transformers is handled.
Oh, okay. Let's go. Let's just do it really quick. I think I have a picture. No, I don't have. Okay. The perimeter of the building, the station building, the Bree Street face and Lakeshore face, is a plenum for delivery of. Actually, you can see it here with the deluge system. A plenum for delivery of ventilation air, primarily for the transformer pockets. What we have, can you see my mouse? On the
Yep.
There's a park on the roof of the station that's accessible to the public, and on the park side of these stacks is intake vents to be able to take air from the park, and it travels due to negative pressure in the transformer pocket down into the transformer pocket through filters, and allows for air circulation in the pocket. The pocket's closed. There are 5 cooling towers associated with each transformer. So hot SF6 gas, which is providing the insulating and the cooling, goes through these cooling towers, and hot air basically circulates within the room and then mixes with the cool air coming out off of the park, and then exhaust fans suck that air from the transformer pocket, and then it is blown onto Bree Street and Lakeshore Boulevard through the cladding. You can see this cladding here. It's called Corten steel, and the Corten steel is perforated. It is perforated to allow the flow of the hot air out of the transformer pockets. It is also perforated in a pattern that evokes the railway land plan view from approximately 1910. So it's essentially public art that serves the purpose of allowing us to ventilate the transformer pockets.
Very elegant. An elegant design choice.
Should have had a picture.
Yeah. We're up on the hour, so I think that let's go ahead and end it there. But Tom, thank you very much for this wonderfully thorough and detailed presentation. It really is a remarkable accomplishment to get to the end of this whole process. And thank you for sharing the story with all of us. Much appreciated.
And thank you, Dan. Thank you for the opportunity to address your members, and I hope everybody enjoyed the presentation.
Absolutely. We will make the presentation and the recording of this available to EEI members afterwards, and circulate that here in the next week. So once again, thank you, and thank you to everybody that joined today.